Okay, so today we will go to system GLS estimation. Okay. Okay, so we finish. Well, so far what we have done is for single equation, we looked at instrumental variable regression and two-stage least squares. Then we went into setting up the system of equations, and we went over system OLS estimation. Today, we'll move to system GLS estimation. Okay, I'll share the screen. Okay. I first listed what our model is for specific observations from the sample. We denote an observation with a subscript I. So for a random draw I, we have the equation y sub I is equal to xi beta plus u sub I. Okay, those symbols in boldface indicate that the they refer to matrices or vectors. So for example, for y sub I, we have g by 1. So we have g equations. So we have g response variables. Therefore, we have g equations. Okay. For each equation, we have the explanatory variables. So these explanatory variables we can put in a matrix x sub I. So this would be g by k. Okay. So you have g equations. You have explanatory variables for each of the equations, and you have a total of k parameters in the total k parameters. K here would be the sum of k sub 1 plus k sub 2 down to k sub g. Okay. And then we have beta is k by 1 and u sub I is g by 1. Okay. For now, we are assuming that we do not have cross equation constraints. Okay. So our observed data would be the set of all x sub I, y sub I going from 1 to n, where n is the sample size. We still have the same model in system GLS. Okay, when GLS on the system of equations means that we're doing generalized least squares, and this allows for accounting for taking into account different unconditional variances across equations. So along the diagonal of the variance covariance matrix, these diagonal elements can differ. It need not be constant. And also, you can have non-zero unconditional variances, covariances across equations. Therefore, the off-diagonal elements need not be zero. We do not consider cases where the variance covariance matrix is a function of x sub I. Okay, so these elements here are not functions of the explanatory variables. Okay, we will derive the GLS estimator and then look at the asymptotic properties of GLS. Okay, let's lay out first our notation for the variance covariance matrix. Okay. We have G equations in G equations, and for each equation we have a disturbance term. So this vector U sub I is actually G by 1. Okay. So the G by G unconditional variance covariance matrix omega is defined as the expected value of U sub I transpose. Okay. U sub I is G by 1. U sub I transpose is 1 by G. Therefore, you have a G by G matrix, and it will be of this form. Okay. Note here, okay, so along the diagonal, we have the variances of the disturbances. Off diagonal, we have the covariances. Note that this matrix is symmetric. So I have sigma sub 1, 2 is equal to sigma sub 2, 1. Therefore, I just denoted this as sigma sub 1, 2. Okay. Sigma sub 1g would be equal to sigma sub g1. So I denoted this entry as sigma sub 1g. Okay. So note this column is just this row, the first row. The second column is just the second row also. And the last row is the same as the last column. We also assume that this matrix omega is non-singular, therefore its inverse exists. Okay. Usually we assume that the expected value of U sub I is 0. This is an innocuous assumption when the equations contain an intercept. So the non-zero components of the disturbances will just be absorbed by the intercept. Okay. Since we're taking GLS, in contrast to feasible GLS, which we would take later, we assume that this omega is known. Okay. Then we would derive the GLS estimator. As you would see in most of the estimation techniques that we would be taking, it is just transforming the problem into an OLS problem. Okay. We transform the equation to remove correlations in error and make the variances constant, actually unity. Okay, this is our original model for a random draw. Y sub I is equal to X sub I beta plus U sub I. Okay, then we pre-multiply both sides to the equation by omega to the minus 1/2, where we would define omega to the minus 1/2 as a symmetric matrix that satisfies some conditions. Okay, so suppose we can do the multiplication. We pre-multiply both sides of the equation by omega to the minus 1/2. What is that omega to the minus 1/2? Okay, omega to the minus 1/2 is such that if we multiply omega minus 1/2 by itself, we get the inverse of omega. So in a way, is loosely speaking, excuse me. Loosely speaking, omega to the minus 1/2 is the square root of the inverse matrix. Okay. And furthermore, if you pre-multiply omega by omega to the minus 1/2 and post-multiply by the same matrix, you get back the identity matrix. Okay. We would use these properties of omega to the minus 1/2 in deriving the GLS estimator and its properties. Okay. Then let's define new variables. xi star would be omega inverse x sub I. So this we define simply uh, okay. So this we define as x sub I star. Okay. And for y sub I star, we define this. Okay. And for the new disturbance term u sub I, we have this. Okay. Then we can rewrite this equation as y sub I star is equal to x sub I star beta plus u sub I star, which looks very much like uh, what we have for the um, original model, right? Except that we have starred variables. Okay. Then let's look at the behavior of the disturbance term. Okay. So we have the expected value of u sub I star transpose. Okay. This would also be a G by G matrix. So this is the expected value. But what is u sub I star? It is this. Okay. So we have omega inverse u sub I. And then when you have u sub I transpose, so you have u sub I transpose omega to the minus 1/2 transposed, but it is a symmetric matrix, so you still get back omega to the minus 1/2. Okay. We assume that we know omega, so we can move the expectation operator over u sub I transpose and have omega to the minus 1/2 outside the expectation operator. Okay. But what is the expected value of u sub I transpose? Okay. What is the expected value of u sub I transpose? Note that we have it here. It is omega. Okay. So this expected value is omega. So we get this expression. But the way we define omega to the minus 1/2, this is just this. So we get the identity matrix. Okay. So the variance covariance matrix of u sub I star would be the identity matrix. Going back to the previous line here, so we have transformed the equation to remove the correlations in error of diagonal elements R0 in this identity matrix. And we have made the variances constant along actually unity along the diagonal of the identity matrix is 1. Okay. So the variance of each of the disturbance term for each equation would be 1. And across equations, the covariances of the disturbances in this transformed model is 0. So we have transformed the problem into an OLS problem. So we apply the system OLS to get the GLS estimator beta. Let's denote it as beta star, the GLS estimator. Okay, I put down here the system OLS estimator. Okay, given the two assumptions for system OLS. Okay. Following the formula for the system OLS applied to this transform model, then for the x's and the y's, we just replace that by the starred variables. Okay. So we have X sub I star transpose X sub I star instead of X sub I transpose X sub I. Similarly, for X sub I transpose Y sub I, we have X sub I star transpose Y sub I star. This is the GLS estimator. Okay. Okay. Then we substitute the expression for X sub I star. Okay. So X sub I star is omega inverse minus 1/2 Xi. Okay. But then we have the transpose here. So the transpose would be omega to the minus 1/2 transpose, but that is a symmetric matrix. So we still have omega to the minus 1/2. And then we have X sub I transpose. And then for X sub I star transpose Y sub I, then we have this first part, X sub I transpose omega to the minus 1/2. Then Y sub I star is just omega to the minus 1/2 Y sub I. Okay. But the way omega to the minus 1/2 is constructed, omega to the minus 1/2 times omega to the minus 1/2 would give us the inverse of omega. Okay. Therefore, this line reduces to this. Okay, we have it here. Omega to the minus 1/2, omega to the minus 1/2 is omega inverse. Okay, I want to get an expression where we can express beta star in terms of beta, because we would like to look at its consistency. Okay. So for Y sub I, the usual trick is you just substitute then the equation for Y sub I, which is X sub I beta plus U sub I. Okay. If you carry out the multiplication, okay, so you have this first term, n inverse the summation of X sub I transpose omega inverse X sub I inverse times n to the minus 1/2 X sub I transpose inverse X sub I beta. Okay. Okay, this, you have n inverse here and then you have the inverse here. So you just get n. So that would cancel out with this n minus 1. And this expression multiplied by this expression would give you beta. And the second term you're left with then is this multiplied by n minus 1/2, the summation of X sub I transpose omega inverse times U sub I. Is that clear? Do you have questions so far?
No, ma'am.
Okay.
And ma'am.
So the trick, so the tricks are just what we had before, except that the notation becomes messier. Okay. Okay, was an interpretation of this expression n to the minus 1/2 the sum of X sub I transpose omega inverse U sub I. Okay. X sub I would be X sub I would be from the sample. Omega we assumed unknown. U sub I is actually unknown, not observable. Okay, but here we have n minus 1. So if we divide this by n, then we have a k by k matrix average. Okay, the dimension of this matrix would be k by k. X sub I transpose is k by g. Okay, so So that's k by g. Omega inverse is g by g. U sub I is g by 1. Yeah. G by U sub I is what? U sub I would be g by 1. Okay. So this should be um, g by 1, right? Yeah. This should be g by 1. This would be k by 1. Okay. This would be k by k. Okay. So you get a k by 1 vector, which is the dimension of beta star. Okay. But if you look at this expression, that is really an average. Okay. That is the population average. That is the sample average. Therefore, assuming this is the sample average, and we know that using the weak law of large numbers, that um, would converge in probability to the population mean. Okay. Okay. So let us assume now that this matrix of expectations is non-singular. Yeah. So this should be. There's some inconsistency here. What is the dimension of U sub I? U sub 1. So we cannot assume singularity if it is not a square matrix, right? So I'll take this. Okay, I'll check that later. Okay. We have consistency of beta star if if the expectation of the second term is equal to 0. Okay. That is the expected value of x sub I transpose omega inverse U sub I is the 0 vector. Okay. But this condition, which I denote by equation 1, is different from the system OLS exogeneity assumption, which is just the expected value of x sub I transpose U sub I is equal to 0. Okay, you have the presence of that omega inverse. In general, this the second equation does not imply the first. Okay, therefore we need for system GLS the modified exogeneity property is the expected value of x sub I Kronecker U sub I is equal to 0. I'll go through the Kronecker product in a while. The Kronecker product condition implies that every element of x sub I is uncorrelated with every element of U sub I. So any linear combination of x sub I, okay, so you would get here a linear combination of x sub I is uncorrelated with U sub I. If this exogeneity assumption holds, that implies that every element of x sub I, all the explanatory variables are uncorrelated with every element of U sub I. And if that is so, then any linear combination of the X sub i's would be uncorrelated with U sub I. But, but if you look at X sub I transpose omega inverse, you are just forming linear combinations. So these linear combinations of X sub I would be uncorrelated with U sub I. Okay. Um, did you have the Kronecker product? Okay, so I'll
No,
just
ma'am.
write the um, definition of the Kronecker product. Okay, I'll shift to the whiteboard. Okay, what is the Kronecker product? Okay, so we have the Kronecker product. Okay, the order of the matrices matter. So the notation for Kronecker product is this. So it's a circle with X inside. Suppose we get the Kronecker product of matrix A and B. Okay. So this is quite simple. Okay, so let's write the A matrix. Suppose we have 1 sub n. Okay. We need not have uh, okay, we need not have a square matrix for A. Okay. And then we have A21, A22 down to A2n, and so on to AM1, AM2 down to AMN. Okay, then for the what you do for the Kronecker product is just multiply each of the entries of A with the matrix B. Okay, so you would you would get a big matrix. Just make sure that yeah, so you'd get a big matrix. Okay. Okay, this is sometimes called also the tensor product. Sometimes the direct product. Okay, so what do we have for the so for the exogeneity, for SGLS1, then you have for exogeneity, the assumption is the expected value of X sub I cross U sub I is equal to 0. Okay. X sub I is G by K. U sub I is G by 1. Okay. Okay, so the exogeneity assumption then says that every element of X sub I would be uncorrelated with U sub I. Okay, so you can rewrite this in this expanded form to see what this assumption means. Okay. Okay. Any questions so far?
None
Question
po.
about the tensor product or yung Kronecker product. So
Tensor
if
product or direct product, alternative names for Kronecker product.
yes po, my question lang po ma'am is that pwede po pala mag-multiply kahit kunyari G by K by G by 1
Note that A sub 1, 1 are
scalars?
scalars, right?
Yeah.
Be, because those are the elements of the matrix A. So you have to write out the elements of X sub I. So this is G by K. So for each equation, you write out the explanatory variables.
Mm. So, ma'am, yung product po na 'to, this consists of a matrix that contains, M times N G by 1 matrices, gano'n po ba 'yun?
The dimension B would be, let's say B is, so I have A is M by N. Um, so I have A is M by N. B, um, B can any B can be any dimension because you're just multiplying by a scalar, right? Right?
Yes po.
So suppose B is P by Q. Okay. Okay, so B here is P by Q. So this whole thing is P by Q, right? But this is also P by Q, P by Q. So the number of columns would be
M times P
M
ano,
by Q,
by M by Q.
right? The number of columns of A is M, but then you multiply by B. So you would have Q columns. And for the rows, you have, sorry, this should be N. Then you have M by P, right? You
Yes, ma'am.
have M, but for each of the elements here, you multiply by um, P, P rows. So you have M times P. Okay.
Got it, ma'am. Thank you po.
Okay. So you get a big matrix. Okay. So I'll go back to the, okay. Okay, so the Kronecker product condition implies that every element of X sub I is uncorrelated with every element of U sub I. This exogeneity assumption implies this, okay? As I have explained here, the Kronecker product condition implies that any linear combination of X sub I is uncorrelated with U sub I, but here you're just forming linear combinations of X sub I. Okay. This exogeneity assumption implies that a variety of GLS estimators, even with a misspecified variance matrix, will be consistent. Okay. We will see that later. Also, this assumption, this exogeneity assumption, is used to justify ignoring estimation of omega. Okay. The second condition is the rank condition. We assume that omega and this expected value of xi transpose omega inverse x sub I are non-singular. Okay, this is a square matrix. This would be k by k. Yeah, k by k matrix. Okay. So this is I think this is wrong. What we have here is wrong because this is not a square matrix. It is x sub I transpose omega inverse x sub I. Okay, and then we have the theorem under the two assumptions, the exogeneity assumption and the rank condition for system GLS. System GLS on a random sample is consistent. That is beta star is equal to beta. Okay. If we do not have the first SGLS assumption and we just have the system OLS exogeneity assumption, GLS would generally be inconsistent. Okay. So for the consistency of GLS, we need this exogeneity assumption, okay, not the system OLS assumption. Okay, let's see the difference. Okay. Suppose you have two equations, so G is equal to. For consistency, let us assume this is the inverse matrix of omega. We assume that omega, using the rank condition, is non-singular. Therefore, this inverse exists. And we denote the elements of omega inverse as omega sub 1, 1, omega sub 1, 2, omega sub 1, 2, omega sub 2, 2. Okay, the elements in this matrix are scalars. And note that this is also symmetric. Okay. If omega is symmetric, then its inverse would also be symmetric. Then let's get omega inverse x sub I. Okay. Okay, so this is our omega inverse x sub I. We have two equations. Okay. And this is our x sub I. Okay. So to be clear about this, first specify what is the beta matrix. Okay. So this is the x sub I1 is the row of explanatory variables for the first equation. X sub I2 is the row of explanatory variables for the second equation. And if we multiply these two matrices, we get this. Okay. Okay, so, yeah. Okay, you can easily do the matrix multiplication. Okay, then let's get omega inverse x sub I transpose. Okay, so the transpose of this multiplied by u sub I. Okay. Well, I have the transpose here, but that gives us x sub I transpose omega inverse u sub I. Okay. So that gives us x sub I transpose omega inverse u sub I. Okay. And for consistency, we should get the zero vector. Okay. Yeah. Okay. So okay, so if you get the transpose of this and multiply by u sub I, you get this expression. Okay. So note that this is a 2 by 1 matrix. Okay, so this is wrong then, definitely. As the examples show, we have a 2 by 1 matrix. What is x sub I? X sub I is g by k. Okay, so let us delete this. Okay. Okay, so if we want this condition to be satisfied, then this should be equal to 0, 0, 0. Okay. Okay, when would this be 0? Okay, suppose sigma sub 1, 2 is equal to 0. Cross equation disturbances are uncorrelated. This would be true. Okay. Omega would have these elements. Okay. Omega would have these elements. So for the 2 by 2 um, two equation case, then you would just have this part. Okay. So suppose the off diagonal element is equal to 0. So that means that the disturbance in the first equation is not correlated with the disturbance in the second equation. Okay. So we just have a diagonal matrix. Okay, so we'd have here in the example. Okay. So if omega 1, 2 is equal to 0, that would hold if and only if in the inverse matrix, you also have omega sub 1, 2 is equal to 0. Okay. If the cross equation disturbances are uncorrelated, then the exogeneity assumption we need is only that the explanatory variables in a given equation is uncorrelated with the disturbance term in that equation. In that case, then the GLS estimator is OLS equation by equation. In the general case, though, if sigma sub 1, 2 is not equal to 0, there's correlation between the disturbance term in the first equation and the disturbance term in the second equation. So suppose you have in the Schur model, suppose you have the demand for goods, quantity demanded for each good are your equations. Well, exogenous shocks to the demand for, let's say, food might also be affecting the the um, the demand for um, transportation. Okay, so it's possible that the disturbances across equations are correlated. Okay, then we would need the covariates in each equation to be uncorrelated with disturbances in each equation. That is what is meant by SGLS 1. Okay, the covariates in each equation is to be uncorrelated with disturbances in each equation. Okay, that is what this says. Okay, then let's work on the asymptotic normality. Okay. Okay, so far what we have done is um, we have laid out the assumptions for system GLS, obtained the estimator, the system GLS estimator, and have looked at the result that it is consistent under the two assumptions for system GLS. Okay. Now let's work on the asymptotic normality. Again, this is a large sample property. Okay. 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 This the notation would be very. The results would be very similar to what we have for system OLS, except that we now get expressions involving omega. Okay, which we assume to for now to be known. Okay. Okay, so you would get um, working with the start variables, we would get this relationship n to the minus 1/2 beta star minus beta. Okay, so that's the distance between the estimator and the parameter you'd like to estimate is equal to this expression. Okay, you can get this from, well, we derived the GLS estimator using start variables initially. And then using what we had for OLS, then you get the similar result, except that it would be in terms of start variables. Then you write out the start variables in terms of x of I and omega. So you would get this expression. Okay, let A be the expected value of x of I transpose omega inverse x of I. Okay. Okay. Then we do the same trick. Okay. The left hand side is we just carry over what we had for the first equation. Okay. So for the right hand side, we we just have the trick we used before. Um, we added A inverse times this matrix, but also subtracted it. So we're really retaining the original expression. Hmm. Um, Let me check. I'm not sure about this. Um, Hold on. The asymptotic naman. Excuse me. Okay, that's correct. Okay, since we have already in terms of U sub I here. Okay, yeah, I got confused because we already have the beta here. Okay, so you really should be well, you get it from here. Beta star minus beta. So we're left with this expression. Okay. You have beta star minus beta times the square root of n. So we were left with this expression. Okay, so we're left with this expression. And then we added and subtracted the same quantity. Okay, but it is this multiplied by this. Okay, okay. So you would get the first term, and the second term would be an expression that converges to 0, converges in probability to 0. Therefore, you would have n to the 1/2 beta star minus beta using the central limit theorem would converge in distribution to the normal distribution would mean 0 and variance covariance matrix A inverse B A inverse. Okay. Note that A and B are different here. Okay. A for system OLS, the A would just be X sub I transpose X sub I. For GLS, A would have this omega inverse. Okay. For B, the B here now is the variance of X I transpose omega inverse U sub I. Okay. And this would be the expected value of X sub I transpose omega inverse U sub I times the transpose U sub I transpose omega inverse, because that is symmetric, times X sub I. Okay. Note that we have a more complicated expression for the variance covariance matrix of these transformed residuals. Okay. Under the assumptions of SGLS and the exogeneity assumption of OLS, GLS need not be more efficient than system OLS. Okay, so later on you will see when GLS will be more efficient than system OLS. Okay, so this would be system GLS. Okay. In practice, we usually do not know what omega is. What is that variance covariance matrix of the disturbances? Okay. In practice, we do not usually know this matrix because these disturbances are actually unobservable. We do not observe that. So we usually find some way of estimating omega or the variance covariance matrix. So we have it here. And if you substitute that estimated variance covariance matrix, then you get feasible GLS. Okay. In feasible GLS, an estimator of omega is used. Let that be omega hat. So that is a G by G matrix. And we usually want that estimator to be a consistent estimator of omega. Okay, so the PLM of omega hat is omega. Okay, how do we get an estimate of omega hat? Okay, we cannot do GLS because we do not know omega. So we usually start with system OLS, let beta check, I think this check, be the system OLS estimator and get the residuals, the OLS, the system OLS residuals. Okay, so this is a U sub I inverted hat. Okay. And then have our usual estimator for omega, but now using the OLS residuals. Okay. That would give you an estimate of omega hat. Okay. Okay. Okay, U sub I inverted hat is, okay, so it is this Y sub I minus X sub I beta inverted hat. Okay. But the trick I use is I subtract minus X sub I beta, but also add it back. So I still retain this equation. Okay. But Y sub I minus X sub I beta, if you look at our model, is just U sub I. So we have U sub I minus this third term, minus X sub I beta hat minus beta. Okay. And if you get U sub I inverted hat, U sub I inverted hat transpose. Okay, so this is G by 1, and you have U sub I inverted hat transpose is 1 by G. So you get a G by G matrix. Okay. So if you carry out, if you multiply this by the transpose, then you get this expression. Okay. So you get U sub I transpose, okay, minus U sub I, then you multiply it by the transpose of this, okay, then minus this multiplied by U sub I transpose plus, then you get this quadratic term, okay. So just verify that you get this result, okay. Okay, then if you substitute it, this expression, you get the summation. Okay, substitute it here. Then you get n minus 1, the summation of this term, plus other terms which converge to 0. Okay. Okay, under SGLS1 and SGLS S system OLS1, the exogeneity assumptions of OLS and GLS, then you have n to the minus 1/2 omega hat minus this is equal to a number that, no, terms that converge in probability to 0. Okay, you just get this from the previous equation. So you have omega hat minus this times n to the 1/2 is this. Okay. Okay, so this is just, this equation just leads to this. Okay. This says that for performing inference about the elements of omega, you can ignore the estimation error in beta inverted hat, the OLSS estimator in large samples. So this is not sensitive. This estimator for omega is not so sensitive to errors in the OLS estimator. Okay. This is useful for testing zero covariances, constant variances, no correlation when you're testing about omega. Okay. Okay. So we have this FGLS estimator. Okay. Okay, so for the FGLS estimator, then it's just the GLS estimator. Okay. We had the GLS estimator, this or this or this. Okay. But we substitute omega hat for omega. Okay. So we get this expression. Okay, so we get this expression. So the feasible GLS estimator is just the GLS estimator where you substitute omega hat for omega. Okay. Then using the usual trick, you substitute x of I beta plus u sub I for y sub I, and you get this equation. Okay. Now let's look at the consistency of FGLS. Okay, so note the following. N inverse okay, let's have this expression. N inverse, though, so I'm really dividing by 1 over n, the summation of x transpose omega hat inverse x sub I minus the same expression except that I have omega instead of omega hat. So I'm just picking up this expression. Okay, so I'm just picking up this expression. Okay, and have it here. Okay. And then divide and then subtract a similar expression but now with omega instead of omega hat. So you can rewrite the left hand side as n inverse, the summation of x sub I transpose, then the difference of omega hat minus 1 and omega, and the inverse of omega x sub I. Okay. Then next we have the vectorization of a matrix. In the vectorization of a matrix, you're just stacking the columns. Okay. And we have this relationship. Okay, I'll go back to the whiteboard to show what the vectorization is. Okay, so what is the vectorization of a matrix? Okay, so suppose we have the A matrix is A11, A12, down to A1N. A21, A22. Can you see the whiteboard?
Yes po,
Yes
ma'am.
po.
Yes, ma'am.
A22 down to A2N, so on to AM1, AM2, down to AMN. Okay. So you have N columns and you have M rows. What is the vectorization of the matrix A? Okay. Okay, so you stack up the columns. So that's really A11, A21, down to AM1, A12, A22, down to AM2, and so on to A1N, A2N, down to AMN. So you just vectorize. Okay. Since you have a long column vector, usually it's easier to write this as A11, A12, down to A1M, A21, A1N, AM1, A12. Oh, hold on. So this is wrong. Mhm. I should have the columns. So that is A11. Mm. So that is A11, A21, down to AM1. That's the first column. A12, A22, down to AM2. Um, Down to the last column, A1N, A2N, down to AMN. And then you put transpose. Okay, so you get the same vector. Okay, that is what we mean by vectorization. Okay, that is the entries of A are stacked column wise, forming, in this case, a vector of length m times n. Okay. Okay. Let us go back to the lecture. Okay. So for vectorization, we have this result on the vectorization of the product of three matrices A, B, and C, assuming that these matrices are conformable for matrix multiplication. Okay, and this would be equal to the Kronecker product of C transpose A times the vectorization of B. Okay, so you pick up C, get the transpose, so you have C transpose Kronecker product A times the vectorization of the middle matrix B. Okay. Okay. Note that in Kronecker products, the order of getting the product, the order of the matrices matter. Okay. Just like in ordinary matrix multiplication. Okay. Under the assumptions of SGLS and our earlier result that omega hat is equal to n inverse times this plus a term that converges to in probability to zero. So this is where did we have that? Lambda hat. Here we have this. Okay. So we had this result. Okay. Okay. Okay, so if we vectorize n inverse summation of x sub I transpose omega hat inverse minus omega inverse x sub I, okay, so we vectorize this, okay. Then we apply this result on vectorization of a matrix. Then you get this expression, okay. So you get n inverse the summation of um, C transpose. So you have C transpose, but that C is X sub I. So you get X sub I, Kronecker product A, but A is X sub I transpose. So you get this times the vectorization of B, the middle term. Okay. And this turns out to be bounded in probability. This term is bounded in probability, and this term converges in probability to zero. And we know, I think we had a lemma before, if you have this, the product of this would just be a term that converges in probability to zero. Okay. Okay. For this equation then, this is just the vectorization of this expression. Okay. Okay, then we know that the terms in this vector would approach zero in probability. And then we have n to the minus 1/2, the summation of x sub I transpose omega hat inverse u sub I minus x sub I transpose omega inverse u sub I. Okay. Okay, so um, okay, so the difference here is in these two terms is just that you have omega here, the population omega. Omega hat here is the estimator. Okay. So you can rewrite this left-hand side in terms of, in this form. You just group together, well, you factor out x sub I transpose and also u sub I. Then you get this expression. And then apply the vectorization, okay? And you would get this expression. And again, you get an expression that converges in probability to zero. So if we combine these two results, okay, um, okay, so we have um, n n to the 1/2 beta hat minus beta. Okay, so you can get it from here. Square root of n beta hat minus beta, then you get this expression. Okay. But then, so you get this expression. Okay. Um, but what is n to the 1/2 beta star minus beta? Look at this expression. Uh, look at this first expression. Okay. But that is also the, if you look earlier, you have n to the minus 1/2 beta hat minus beta. Okay, if you get this, beta star minus beta, you also get this. Okay. Therefore, if you look at okay, so if you look at this expression, okay, if you look at this expression and look at your previous notes, that is also this n to the 1/2 beta star minus beta plus some term that converges in probability to 0. So what does that say? The asymptotic distribution of n to the 1/2 beta hat minus beta, this, is the same as that of n to the minus 1/2 beta star minus beta. Asymptotically, these two expressions would have the same asymptotic distribution. Okay. One is beta hat here is feasible GLS, while beta star is GLS. Okay. So if you get the difference, this minus this, so if you get the difference, this minus this, you get OP1, or n to the 1/2 beta hat minus beta star is OP1. Okay. In this case, then, from this expression, okay, so this expression, we say that beta hat and beta star are asymptotically equivalent. Okay, so the FLGS estimator and the GLS estimator are asymptotically equivalent, or more precisely, square root of n equivalent, which is much stronger than saying that they are both consistent. Okay. Therefore, you can treat FGLS as if it is GLS. That is the result of this square root of n asymptotics. Okay. Okay, so we've been doing the asymptotics for system GLS. How about the small sample properties? If n is small, the statistical properties of FGLS and GLS can be different. Okay. Now, under the zero conditional mean assumption, GLS is unbiased, but feasible GLS is not unbiased. Okay. Well, that's the price you have to pay for estimating omega. Okay. Okay. Then we have the fully robust variance matrix estimator under under the two assumptions for SGLS. Okay. So here get the FGLS residuals, U sub I hat, and then this would be your estimator for the variance covariance matrix of the FGLS estimator. Okay. As you know, this what to say about to say. Okay. Well, you need the asymptotic variance for test of hypothesis. Okay. This estimator is robust to system heteroscedasticity. Okay. Um, this holds even if you have system heteroscedasticity because we did not restrict um, the diagonal elements to be constant across equations. Okay, it is in the transformed model where it comes out to be one. Okay, so loosely the variance covariance matrix of u sub I conditional on xi does not depend on x sub I. Okay. Okay, so I'll stop here and I'll continue with system GLS, some notes on system GLS, and um, and be more specific about the seemingly unrelated regression model. Any questions? No questions?
None, ma'am.
No, ma'am.
Okay.
Ma'am,
So I'll
question lang.
see you Thursday. So we're a bit behind. I thought we'll finish our simultaneous equations before the Lenten break, but we'll just finish as far as system GLS, I think, and the Sure model. So after the Lenten break, we'll do simultaneous equations. Okay. So the it's just in the system of equations that the notation can be quite messy. But then we're going the through it the system of equations part, so you would be more aware of the assumptions. Okay. Okay. So I'll see you Thursday, same
Ma'am,
time.
question lang
Yeah.
po. On the midterms po, ma'am, like, is there a schedule na po ba?
Um.
Topics na parang you intend to cover po for the midterms?
I'll revise the outline. So it would be up to panel, panel data approaches. Um, After system of equations, we'll do simultaneous equations and then panel data. Um, we will have the limited dependent variable models after your midterm. Okay.
Okay po. Thank you po, ma'am.
Yeah. Because the panel data approach is more consistent with the system of equations approach. Though I'll try to find another approach in the presentation so it would not be too complicated. The one of Wildrich is quite complicated, maybe unnecessarily. Okay, we just have two exams, so it would just be so we'll have the midterm after the panel data approaches. Okay. Okay.
Okay po. Thank you po,
So
ma'am.
yeah. So see you. Be careful. The COVID situation is quite bad.
Po.
Okay.
Sige po. Thank you po, ma'am. Ingat po
Thanks,
kayo.
ma'am.
Thank you,
Po.
Stay
ma'am.
safe.
Yeah. Okay. Bye. Hi, Charles.